Okay, so searching, sorting, and big O. How many, just those of you sitting in this room, how many of you have heard the term big O? Two. Is that from, I don't know if you want to tell, is that from Math 4?
Yeah.
Okay. So here's what we're going to do in our unit on searching, sorting, and big O. We're going to study 7 algorithms, 2 searching algorithms, linear search and binary search, 5 sorting algorithms, and you can see them right here: bubble sort, selection sort, insertion sort, merge sort, and quick sort. I'm gonna have you know these search algorithms and sorting algorithms in excruciating detail. The exercise you're gonna do, I will be the first to admit, it's pretty tedious, okay? But by the time you're done, I think you're going to be experts on all of these sorting algorithms. And as a bonus, I don't know if it's a bonus or not, but there won't be a programming assignment for this. It's just going to be showing me that you understand the concepts of how these sorts and searches work. Okay, so that's the goal. For each of these algorithms, you need to know 3 things. Understand how the algorithm works. And I'm going to go through all this stuff with you in detail also. But for the searching algorithms, you're going to demonstrate by listing the items in the array that will be examined in the order in which they will be examined. Okay, so if you're looking for something in an array, you're going to be looking at items in the array one at a time until you find what you're looking for. You're going to have to tell me what order the items in the array are going to be looked at in. Not sure I got that grammatically correct, but I think you know what I mean. So for the sorting algorithms, you're going to be drawing snapshots of the array over and over again, so you show me what it looks like after each pass through the array. Okay. So that's the main thing, actually. Also, state the big O running time of the algorithm. We'll be talking about that if you have no idea what that is at this point. And then understand the code for the algorithm. Okay. I'm going to be providing a program that provides all of the code for all of the sorting algorithms. So it's not like you're going to have to make up some code, but you're going to have to look at that code and understand what's going on with it. Okay. All right, let's talk about big O a little bit. So computer scientists use big O notation to express the efficiency of algorithms in very broad strokes, like not how many milliseconds it's going to take, not even how many operations is it going to take. We'll talk about it more in a second, but for now, just there are formal mathematical definitions that you will cover in a discrete math class, but we're not going to get that formal about it. For our purposes, we just need to have an intuitive sense for what the big O will be. If I show you an algorithm, you need to be able to sort of intuit what the big O will be, right? In Math 4, hopefully anyway, you're actually like doing proofs and stuff to show that certain functions are a certain big O. So here's how big O works. So we've got an algorithm. Imagine that we have a function that expresses how many operations it's going to take for that algorithm to complete. So that will be a function of n, where n is the number of items being processed. How am I doing so far? Should I say that again? So we're going to imagine, we don't have to come up with this function, right? This would be a really hard function to actually come up with, but just imagine we've got a function of n, where n is the number of items being processed, that tells us how many operations it's going to take to complete the task. That make sense? Okay, because if that doesn't make sense, then nothing else is going to make sense. Okay, so the good news is we don't need to know the exact function. In order to get a really good sense of the efficiency of the algorithm, all we need to know is what family of functions the function falls into. So this is going to I don't know if you hated algebra, you may be getting a little PTSD now, but it's okay. You don't have to know that much. And if what I'm about to say doesn't make sense, we can make it make sense. Okay. But you just basically have to figure out, okay, that function that I was referring to, is that a linear function? Is it a quadratic function? Is it a logarithmic function? What kind of a function? Is it exponential? Okay. That's all we need to know, really, is like which family of functions does that fall into? That's all big O is. Okay. That's sort of my intuitive approach to understanding big O. So how do we write big O? If turns out to be a linear function, we say the algorithm is big O of n, because n would be a linear function, right? If we said f of n gets equals n, that would be, or 2n plus 1, that would be a linear function, right? So we say big O of n. If it turns out to be quadratic, we would write big O of n squared. Turns out to be a constant function, we write big O of 1, and so on. Okay, so that's my high level introduction to big O. Don't really expect you to understand how to apply that at this point. We're just going to do it for each of these algorithms, and hopefully you'll sort of start getting the swing of it, the hang of it. Anybody want to ask a question yet? Okay. So I've got this link right here that takes you to the file that has all of the sorting algorithms, and it actually times them. So it's kind of fun, actually. You can set up how many items you want to have in the array. You can set up how many options you want the randomly generated array to what size of numbers you want to have in the array, and then run it and see how long all the different sorting algorithms take. And here's a link to a website that I found that has animations of sorting algorithms. Okay. We're going to start with the searches. And for almost all of these, maybe all of these, I'm going to be using these same numbers. So just some random numbers that I came up with. Whoops. Actually, let me do it. Search. I guess I'll come over here. So 2, 8, 6. Okay, so there's an array. Wait. That's not what I was expecting. Okay, so there's my array, right? So how does a linear search work? I'm not sure if you've heard. Go ahead.
Starts at the beginning and goes to the end.
Starts at the beginning and then just goes through the list until it finds what it's looking for, right? So what would be the big O of linear search?
O of n.
Yeah, it's going to be linear, right? I mean, that's part of the name of the algorithm, I guess. But and often with a big O, you can think of it as worst case scenario, right? You might be thinking, oh well, if the number I'm looking for is 82, then it's not big O of n. Well, that's true, but what's the worst case scenario, right? If the number I'm looking for is 60, then it's going to the number of operations it's going to take is going to depend on n, not n squared, not log of n, nothing like that. It just depends on n, right? The function's going to have an n in it. What would be so this has 12, 2, 4, 6, 8, 12 items, right? So what would be the average number of, I'm going to say, comparisons I would have to make in order to find what I'm looking for.
Six.
6, right? On average. Okay. So on average, you could say that it's going to take me n over 2 comparisons. Right? So should I say big O of n over 2, or should I say big O of n? Big O of n. There is no such thing as big O of n over 2, because n over 2 is just a linear function, right? So we just say big O of n. We don't care about the 2. Okay. All right. So I think I'm done with linear search. I think you've probably all seen it in one form or another. I don't think we need to actually create the code for that. Let's work on binary search a little bit. So how many of you have studied binary search? In the reading? Oh, is it in the reading? For searching, for the search. Yeah, okay, yeah, of course. Okay. All right, so I'm not going to be able to use a binary search on this array, right? Because in order for binary search to work, the items in the array have to be in order. So I'm gonna go ahead and paste it, and then I'm gonna type the numbers again, except in order. So let me know if I get one wrong. 35, 38, looks like 43, 53, 55, 60, 67. I feel like I've skipped one. Also, I have 82 and 90 and 96.
92.
Oh, 92. Okay, so 82. Whoops. 82, 90, 92, 96. Okay. So now they're sorted. And so I'm going to use a binary search. The way binary search works is basically I'm going to compare what I'm looking for with the middle item in the array. If that's the answer, then I'm done, right? If the thing I'm looking for comes before that, then I'm going to recursively call the binary search function, except just looking in the first half of the array. If the thing I'm looking for, if the target is bigger than the middle item in the array, then I'm going to recursively call binary search again, just looking in the upper half of the array. Okay, so let's say I'm looking for the number 35. The way binary search, so I'm going to actually put some indices on here. Okay, so the way binary search works is I'm looking between 0 and 11, right? So I find the midpoint of those two numbers. I'm going to just add 0 plus 11 and divide by 2. That'll be right, and that's what we do because we're using integers in C++, right? So it's going to be 5. 11 divided by 2 is 5. So I'm going to start by looking at the 55. So that in your homework, what you're going to do, I'm going to ask you what the numbers are that are going to be looked at if I'm looking for the number 35, right? And you're going to say, okay, the first number is going to be 55. 35 is less than 55, so now I'm looking between 0 and 4. So the midpoint of 0, 1, 4 is 2. So now I'm going to be looking at array sub 2. So the second number I'm going to look at is 38. Okay. My target is less than 38. So now I'm looking between 0 and 1. the midpoint of 0 and 1 is going to be 0. So the next number I'm going to look at is the 15. Now I'm looking between 1 and 1, right? Because I know it's less than index 2 and I know it's bigger than index 0. So I'm looking between 1 and 1. And this may sound like nonsense because we're all humans, but the computer is just going to be, okay, I'm looking between 1 and 1. The midpoint of 1 and 1 is 1. So I look at a race of 1 and I find the target. Okay, so that's the numbers that a binary search is going to look at and in the order in which it's going to look at them. Questions about that? Okay. Let's talk about big O. So 12 items. Let's say I had 16 items in my array. What would be the worst case scenario? How many numbers I would have to look at? Let's just for the sake of conversation, let's say I just always am looking for the smallest number. So I would look at a race of 8, right? And then I'd look at a race of 4. And then I'd look at a race of 2. Then I'd look at a race of 0, I guess, right? Because I'm looking between 0 and 1. And then I look at a race of 1. So worst case scenario would be if there's 16 elements in my array, worst case scenario would be I'm looking at 5. Okay. What happens if I double the size of my array? What's the worst case scenario now? 6, right? Because if I've got an array with 32 elements in it, I look at the middle element. Now I've narrowed it down to 16 possible elements. So I'm back at needing 5 more looks, 5 more comparisons. That makes sense? Okay. And so if I have an array of size 64, what's the worst case scenario? How many am I going to look at? 7. All right, getting the hang of it. All right, so let's talk about, so this is algebra. I want to think about what function this is. Here's x, here's y. I mean, actually, I guess I should say here's n, here's f of n. So the question is, how do I write f of n gets something with an n in it, right? But it's going to be easier if we go the other direction. Okay, so I'm going to bear with me for a second here. Let's call this x. Actually, let's call this y, and let's call this x. And can you tell me how to get from x to y? So I'll give you a hint. What if I just reduce each of these by 1? Does that ring any bells?
2 to that exponent.
2 to the x. Y equals 2 to the x, right? Actually, 2 to the y equals 2 to the x minus 1, right? So that's an exponential function, right? Okay. So if I want the inverse of that, right? I know I'm a little scary throwing around mathematical terms here, but I want it to go the opposite direction. What's the inverse of an exponential function? Log, right? Okay, so I know this may be a little scary, but don't worry. If you like hated logs and you thought you were never going to see them again because you finished that part of math, it's not going to be that bad. Okay, there's just one very fundamental thing you have to understand about logs, and that is just that it's the opposite of exponent. Okay, so what we just talked about, that's really all you need to understand about logs. So it turns out that what's going to work for us here is we're going to say y equals log base 2 of x, right? But all we need to take away from that now, like it may feel like things got really ugly really fast, okay? But all we need to take away from that now is just to know that a binary search is going to be big O of log n, and we're done. Okay, it doesn't even matter what the base is. The base is another one of those things that, like a constant, you can throw it away. Doesn't matter. The fact that it's logarithmic is what matters. Okay. So we're going to be seeing that a few times. So really the only thing that you need to understand about logs is for this class is just when you see a certain situation in an algorithm, learn to identify, oh, that's a log, right? Anytime you see an algorithm that's cutting the number of items in half every time, there's going to be a log in there somewhere in the big O. Okay. And you're going to be seeing that a few times. Okay. So bottom line out of all of that is I'm going to say binary search is big O of log n. That's all. That's all we need to know. Anybody want to ask a question? Say that you're totally confused. Ask me to repeat something. Okay. All right. So the only thing we haven't, well, I guess we have done that. We traced through the binary search. We haven't seen the code. Let me trying to decide whether to do it here or in Visual. I guess I'll start up Visual Studio real quick. Geez. Okay, so binary search. Just to keep things simple, I'm going to say we're going to just return the number we find. Okay, and if the number isn't there, we're going to return -1. Okay, not necessarily the best design, but the simplest design. So let's go with that. So in order for binary search, we need 3 parameters. We're going to have an array, and we're going to have a low, and we're going to have a high. Those tell us the range of the array that we are looking at. Right. So when we call binary search to start with, we're going to be looking between 0 and however many items are in the array. -1. Right. But then we're going to be calling binary search recursively and narrowing that down as we go. So what's our base case going to be?
Low equals high.
Close. I mean, if low equals high, that could be a base case, but we can get a more fundamental base case. If low equals high, we can keep going one more time.
Target is equal to the.
Okay, that would be a base case. We found what we were looking for, right?
Yeah.
I guess I need target in here, huh? So I have to admit right now that I thought I had the code for binary search in my notes and it's not there, so we're making this up as we go, but I'm pretty sure we can do it. If target, oh, no, let's do this first. Let's say int mid gets low plus high divided by 2. Okay. If target is equal to array sub mid, then we're done, right? Return array sub mid. I don't know if it feels weird that we're just returning the number that we were looking for. So you may have to just imagine that this is a more complex situation where there's there's numbers, but then there's also a bunch of other data, and we're returning we're returning all the data that's associated with that number. Okay, in order for it to actually be useful. But to keep it simple, we're just going to return the number when we find it. Okay, I'm going to just tell you there's another base case.
Not gonna do right.
Right? And how would you know that?
If low and high are the same thing.
Okay, that's what he suggested. But if low and high are the same thing, that still could be the target.
Right.
But it would have caught that in the first if statement, I suppose. So I suppose that might work. But what I'm going to suggest if we just say if low is greater than high.
Right.
So they've crossed. So we missed it, wasn't that? Okay. Okay. Else, so what's our recursive case going to be? If the target is less than array sub mid,
Right.
we're going to call binary search,
Right.
and we're going to say just look in the lower half of the array. So we send the same array, same target. Low is still low, but instead of high, we're going to send mid -1. That makes sense? Okay.
-1 becomes the new high.
Correct. Yeah. Mid -1 is the new high. Whoa. Now, same thing except the opposite direction, right? Mid +1 becomes the new low. How's that look? Okay. I think I'm going to just go with it. Hope for the best. Okay. If it's not perfect, it's close enough for us to get the concept anyway. Okay. I'm pretty sure that'll work, but I don't want to spend 10 minutes putting it in a real program and testing it. So unless everyone really wants to see me do that. All right. Any questions about how binary search works? Okay.